Hey, good afternoon, folks. We're just going to get started in about a minute or two, so just um, uh, bear with us for a minute. All right, I think we'll get started. Good afternoon, everybody. Eric Ely here, Director of System Operations and Market Design at ESIG. Welcome, everybody, to this webinar. For those of you that are not familiar with ESIG, ESIG is a membership-based nonprofit organization providing objective information, resources, and networking opportunities in support of clean energy and energy systems integration decisions. So we do this through workshops, tutorials, webinars, blogs, working groups, and task force activities, and also producing technical resource materials, including the reports that come out of the different task forces and fact sheets and so forth. So for those of you who are members, thank you for your support. It makes possible these webinars and all the other work that we do. And just as a reminder, our workshops and monthly webinars are open to everybody, so feel free to register and to share with other colleagues. You can find the different webcasts and schedules on www.esig.energy. You can also find ESIG on LinkedIn, YouTube, Facebook, and Twitter. So just a couple logistical matters before we get into it. First of all, participant lines will be muted for the duration of the webinar to avoid unnecessary distractions. We will have a Q&A at the end of the session today, and for that we use the Slido platform. You'll see the Slido link there on the splash screen, as well as the code ESIG6, which will get you to the place where you can ask your questions. So right at whatever question you have on there, you also see the thumbs up buttons next to the questions that you can cast a vote. That helps prioritize the questions if there's a lot of them. We will try to get to as many as we can, and we try to also get to those questions that we didn't have time to after the call and post that along with the recording and PDF. Just a reminder to please be respectful with your questions, prioritize posting questions for the speakers rather than any personal statements or opinions. So we'll keep about 10 minutes at the end for that Q&A. So with that, let me introduce the topic and our speakers. So the forecasts of demand growth that have been projected in recent years continues to show an unprecedented level of new loads. So as many of our ESIG members and close colleagues should know, ESIG has been working across multiple energy systems disciplines through its large loads task force to gather stakeholder input and as part of that develop a set of recommendations for how we as an industry can integrate these large loads onto the power system reliably, efficiently, and equitably. So in this webcast, we will share some of the early work coming out of this effort, as well as some particular considerations on the data needs that help support integration, as well in addition to how the capabilities of loads providing flexibility to the grid, being able to adjust their consumption in times of need, can also support reliability and economic efficiency objectives. So I am joined by two of my ESIG colleagues to help share this work, Julia Matevosyan, who's the chief engineer at ESIG and also the lead of the large loads effort at ESIG, and Trieu, who's a visiting research fellow, who will both present today on the activities of the task force, giving both task force members and others who haven't been as involved in this effort a good preview of one of the first reports that will come out of this group. So again, another reminder to use Slido, slido.com, using the ESIG6 code to ask your questions. Feel free to ask those throughout the presentation, and we'll get to those at the end. And I think without any further ado, let's go ahead and get started. So I'm going to turn it over to Julia, who I believe is going to kick us off. Julia.
Yes, hi everyone. Thanks, Eric, for the introductions. So yes, I'll kick us off here. And as Eric mentioned, this webinar is kind of to cover the first of the reports that will be coming out of ESIG Large Load Task Force. And the report, and as well as this presentation, will cover background information, data and flexibility needs, or the large load integration. So just to set the scene here, in the past century, maybe last 50 years of last century, there was a steady growth of electricity demand, primarily driven by electrifications. And then in early 2000s, due to economic turndown, but also energy efficiency, this demand growth kind of settled at certain level. And more recently, in the past few years, we again start seeing electricity demand growth, but also higher growth is forecasted. If you look at 5 years, that is based on aggregated forecasts submitted to FERC, and GRID strategies are doing this reporting every year. If you look at 2022 forecasts 5 years out, and say 2024 forecasts 5 years out, you can see that forecasted summer peak growth nearly tripled. We are currently awaiting report from GRID strategies for 2025, and even starker growth is expected in that report. Next.
Hey, Julia, I think you need to go and take control from to move the slides.
I'm sorry about that. Can you see my slides now?
We see slide 2.
Yes. Okay. So yeah, just this is kind of the slide that I was talking over a minute ago, and I'm sorry about that. But I think I kind of have it covered. So I'll move to the next one. If we just zoom to ERCOT, being my favorite area, you can see that even if we just look at what's under study in ERCOT review right now for 2030, you'll see there is 70 gigawatt of large loads. And if entire queue is included, where no studies yet are submitted, then it's really a huge amount, going up to more than 200 gigawatt. And just for the reference, ERCOT is currently 85 gigawatt peak system. So the growth is really unprecedented, but there is also a lot of uncertainty in this queues, because there are a lot of exploratory applications where load developers are looking for places where they can connect faster and cheaper, where conditions are more beneficial, and therefore there may be multiple applications for same project in the queue. And so it was found, in our work, that increasing levels of commitment in each step of the interconnection process may help to reduce this uncertainty. Maybe study fees, material collateral, site control evidence, and things like that can add more certainty. Also, maybe finding out which requests are duplicative for the same development. That would be helpful as well. What adds to uncertainty, though, currently is that large load interconnection queue data is often not public. Another thing is that the large loads today are seeking to connect very quickly. So maybe it's 1 to 2 years to develop large load site, whereas significant load growth is putting strain on generation capacity and transmission capacity development. And here you can see the plot on the right-hand side from Elevate and Grid Lab work that is showing kind of how long it takes to develop a large load site versus how long it takes to develop generation and transmission infrastructure. And you can see that there is this misalignment between how fast loads want to connect versus how fast industry can keep up with that. And so with all of that motivation in mind, we started our large load task force at the end of last year. And the topics of the task force cover multiple working groups within ESIG. So it's reliability working group, system operations and markets design working group, as well as system planning. And we structured the task force as 7 different project teams. One is focusing on interconnection process and studies. One is focusing on interconnection performance, what requirements that are needed to ensure reliable operation of large loads and reduce any unwanted impacts on the grid. Modeling requirements, so this is primarily focusing on how large loads should be modeled for stability assessment, large load forecasting, so the word speaks for itself, and this is forecasting looking longer term, so it's not operational forecasting that we're covering here. Transmission planning, how to consider large loads as we are planning transmission, resource adequacy, again, how large loads should be included in resource adequacy assessments, and market and operations. So this is looking at how market design and operations need to change considering large load growth, but also that many of those loads coming with co-located generation. So this is a timeline for reports now. So we've been working continuously throughout 2025. And currently, all of the project teams are in the process of drafting their reports. You can see the timelines. As I mentioned in the beginning, the introduction report is, we expect the draft to come out sometime by the end of December. But because this report is kind of precursor to all of the reports, we expect that we'll be continuously updating it as other reports are coming out. And so we'll publish final one kind of concurrently with the last report from Large Load Task Force. And on a little bit faster timeline right now, because of industry need, we'll have a large load forecasting report, which is looking at methodology and framework for forecasting large loads. And the final draft of this report is expected by the end of November, and final report mid-December. So again, this one is going a little bit on faster timeline because it was kind of dictated by industry needs. And the other reports you can see, they will be coming out throughout Q1, Q2 of 2026. You can just use the slides for your reference. All right, so for introduction report, as I mentioned, the idea was to cover background and context for large load development, again, so that not every report has to repeat the same thing multiple times. So we'll be talking about kind of how demand was growing historically, what is causing rapid demand growth right now, what are the drivers, what's different about modern large loads, why are we talking about this now and not previously, what are system level impacts from large loads, and then we'll also focus on some of the cross-cutting areas that cut across all of the project teams and areas of focus, and we'll talk about data needs and availability of data, as well as large load flexibility, what's possible and what's needed. And yeah, as I mentioned, the draft report will come out soon. So what is different between about modern large loads? This, of course, size and concentration. The individual facilities can now reach from hundreds to even gigawatt scale. They tend to cluster in regions, and this is driving localized reliability and stability challenges. These new loads, due to their size, they are seeking connection to high voltage levels at transmission level, and that has impact on interconnection process compared to how those were treated historically. As I mentioned, the growth is rapid and uncertain, so I will not stop there. You've seen the charts in the beginning of my presentation. Demand profiles are different from what we used to see before, where we had like flat 24/7 profiles. Now we can see highly dynamic swings. Especially AI training and electrolyzers can kind of swing tens of megawatts or sometimes hundreds of megawatts in seconds. Demand response potential exists, but due to business cases of the large loads, it's not necessarily easy to unlock. And many sites feature co-located or backup generation, but again, there is no certainty yet of how this flexibility can or cannot be used. And then these loads are power electronic interfaced, which may add stability risks because the AI encryptor sites may switch over to backup supply during system faults. And it was also noticed that AI training cycles can introduce oscillatory behavior and again impact grid stability. So we need new standards and models and screening tools to study these issues and detect them in a timely manner. So all of this is to say that modern large loads, they behave less like traditional loads that we've seen previously and more like inverter-based resources that we've seen proliferating in the past 10 to 20 years. So all of this requires new planning, modeling, performance, and interconnection frameworks. So we pondered a little bit about defining large loads. How do we want to do it for the purpose of ESIG Large Load Task Force? And then basically agreed to adopt similar definition to what NERC Large Load Task Force decided to do. NERC Large Load Task Force actually did a survey of stakeholders trying to define the size of large loads, and that's specifically for for NERC functions. And 75 megawatt load was named as kind of more commonly something that's considered large load, but NERC actually limited itself to this higher level definition, saying that it's commercial industrial facilities that can pose bulk power system reliability risks due to their size, operational behavior, or control systems. And this is to say that, in different systems, what's large and what's impactful can be different. And even within the same system, depending where the large loads are connecting, in a say, stronger grid, large size load will not have big impact, whereas in a weaker grid, even smaller size electronic load can have significant impact. So again, in ESIG Large Load Task Force, we decided to adopt this high-level definition and focus more on impact than size. We also designated this high-level characteristic large load categories based on characteristics, and so this is data centers, oil and gas mining, emerging industries, hydrogen, and fleet electrification. And again, this is not to say that this is the only way large loads can be categorized, but we wanted to set up the framework for other project teams within ESIG Large Load Task Force to kind of work around and make sure that we are all using the same terminology throughout the reports. We try to classify importance of different large load characteristics on components of grid planning and operations. And this category is, again, something maybe a little bit subjective. We're still working on this, but we work through the scale of importance from, must consider this detail, should consider, may consider, or just keep track of this detail. And we focused on large load size, geographic concentration, development uncertainty, profile flexibility, co-located resources, so co-located generation, and then if the load has power electronic interface. And we evaluated the impact of these characteristics on each of the topics of focus of large loads task force. And so, yeah, that's how the table looks like now, but it's still subject to change. We need to agree across all of the project teams. Talking about data needs, so we tried in each of the area of focus identify what data needs are. Again, we're still kind of finalizing this, but at high level for load forecasting, you need load type, profile siting, demand growth trajectories, and what are the drivers for adoption. For interconnection process, it's important to know electrical characteristics of the loads, write-through behavior, ramp rates, what kind of backup, and need models that you can plug into interconnection studies. For interconnection requirements, again, you need to understand write-through capabilities, how controllable these loads are, how flexible they are to modulate, and are they compliant with any kind of voltage and frequency support obligations that may apply in the area. For modeling, kind of self-explanatory, detailed, dynamic, and steady state models are required, and the models should include all of the important details for the study area focus. For market operations, primarily flexibility options are important. For transmission planning, it's geographic concentration and siting, temporal coincidence of demand growth, and what are the likely expansion scenarios. And for resource adequacy, we need to know what's the forecast uncertainty, what is coincidence with system peak, what is flexibility during scarcity events, and what is the available flexible resources. There are several challenges with data availabilities. Load developers often treat the information as proprietary, and that hinders the accuracy of forecasting. In the interconnection process, utilities frequently receive incomplete information, and so system studies are made based on some assumptions. And that, on one hand, may lead to overly conservative results, because system operator or utility on their side may decide to assume information and keep some margin. But on the other hand, if the assumptions, again, are not realistic, it may have a reliability impact. There are no standardized models for large loads. This is still active area of research and development, but what's happening now is that system planners, they are using models approximating the behavior of these power electronic loads. And again, that can be either overly conservative or may have potential reliability risks. Market relevant data on price sensitivity, operational flexibility, or willingness to curtail is generally not available and is not systematically collected. So this is something that's really needed. For transmission planning, siting information and long-term expansion trajectories are uncertain. And again, it's often tied to confidential information, corporate strategies. And for resource adequacy, the most acute gap right now is representative 8760 demand profiles. And then again, information about elasticity and flexibility of large loads. So addressing these data gaps requires data sharing frameworks, standardization of load modeling, regulatory or market mechanisms that incentivize this transparency of data and data sharing, while also balancing commercial sensitivities of large load developers. And with that, I believe I turned over to Trieu to take us on discussing flexibility needs.
Thanks, Julia, and thanks everyone for tuning in here. So one of the things that we quickly realized as a team, as Julia already noted, data needs is something that cuts across all of these components of grid planning and operations in the slide she showed earlier. But the other aspect that kept coming up was flexibility. So how flexibility of large loads can be incorporated in these aspects, or might impact the ability for transmission planning studies, and results from transmission planning studies, for example, could be very impactful. So this is a chart that Julia showed before, and it really cuts across all of these areas. So hence, we decided to lay out the framework around flexibility within our introduction report, and each of the follow-up reports will take a deeper dive on these aspects. So of course, one of the first things one has to look at is a definition of what load flexibility is. So we developed this initial definition that is broad on purpose in order to encompass all aspects of flexibility. And essentially, it's the facility or the consumer's capability or commitment to at least temporarily change their net consumption of electricity to better match, grid service needs or the need of the grid overall. And that net consumption is important to be able to cover, facilities with on-site generation or on-site resources, or even, agreements with different front of the meter resources that could also provide some of the grid service value. So that's a definition of flexibility that we were tuned to. And what we tried to unpack is some of the reasons why one might explore flexibility, as well as some of the challenges, and we'll get to that at the rest of these slides here. So why include or why consider flexibility from a grid perspective? Flexibility can reduce or defer transmission upgrades and associated costs. Same thing on the generation side, and ultimately also enable more options for reliability grid services and reducing the cost for the provision of those resources. You tie those first three bullets together, and you have the potential for improved reliability and overall lower system costs on the electricity system side. That's the grid perspective. From the load, I'm sure everyone on this call has heard of speed to power, speed to market, and that is a prime driver of flexibility from the load side, which is to reduce the timelines to interconnect those new facilities, as well as lower the interconnection costs. There are opportunities, of course, to reduce energy costs to the load, as well as creating additional sources of value through kind of DR programs, et cetera. We'll talk about some of the challenges next. There are broader societal impacts I won't touch on. Obviously, an important one is ratepayer costs and the extent to which those electric system costs on the grid side, roll over and transfer to ratepayers is an important consideration, of course, for all ratepayers, not just the load side. Ultimately, though, I think Julia laid this out in the beginning here, which is we're in a situation where load growth is, potentially significantly outpacing the growth of supply. So really, the discussion around flexibility is, can we change demand so that we can make more efficient use of those limited or scarce supply resources? Of course, it's not all rosy. There are certainly challenges to implementing flexibility. Julia, listed some of those early on. I've unpacked this in kind of four broad categories. One is cost, both opportunity costs. As Julia noted, some of these customers have a very high lost revenue when curtailing data centers for curtailed computations, for example, and even scarcity prices on the electricity side will not overcome that potential lost revenue for the computations that they're making. Direct costs also to enable flexibility. On-site resources require capital investments or fuel investments, depending on the on-site resources that could add to the overall cost of the load. Business models, multi-tenant data centers are one example where service level agreements make it difficult for the different data center owners or operators to be able to enact those flexibility provisions that we discussed earlier. And then institutional issues associated with market participation rules in energy markets, as well as kind of controllability and dependability from a system operator perspective. And finally, technical constraints. There are a variety of reasons why you may not want to curtail your electricity consumption, as it might impact the operations for your primary business. So I listed a few here, and they're important to consider when we talk about the flexibility potential from large loads. But there's also a unique opportunity with respect to large loads specifically. Some of these overlap with the unique aspects of large loads that Julia listed. One is the large and concentrated nature of these loads. Both they have a bigger impacts, both positive and negative, and therefore enabling them to be flexible can enable more positive impact from a grid perspective. Secondly, that concentration, both in terms of the number of facilities and firms, could facilitate an easier agreement between the customer side and the grid side for this flexibility, instead of dealing with thousands or millions of potential customers having the same impact. Ideally positive through a few facilities or a few firms could really make it easier to have those transactions. Technical flexibility, the speed at which some of these large loads can change their outputs really enables more grid services that they could provide. Of course, there's some downsides to this. I think we've seen some examples where quick changes can have a disruption on the grid reliability side. Nonetheless, if channeled correctly, that flexibility and would unlock a faster response to provide reliability services. The third bullet here is around just the sophistication of some of these facility owners and operators, really enable them to perhaps more easily participate in some of these complex processes and agreements with utilities and others. Nonetheless, what our perspective here is, a lot of these issues, if we can overcome them, may be beneficial to transform demand side flexibility for all loads and not just large loads. So that's something to look out for. Okay, it looks like I got some interruption here on the slides. Fundamentally, we wanted to lay out what can happen in terms of what are the specifications one might need to enable flexibility. So here's a little framework on the 4 hows of flexibility. How early, so what is the ramp rate? What is the notice and notification that loads will be needed in order to be able to operate flexibly in the time that the grid or the system operator requires? How long the duration in which that flexibility is called upon, minutes to hours, etc. How much, and this is bidirectional, so this is the percent of the energy that is consumed, 25%, 50%, or megawatts, in both directions. It could be increasing or decreasing your load, especially with backup generation that really gives a controllability in both directions. And then how often, how frequently. Is it continuously called upon in terms of a regulation service type, or if it's event-based, more for an RA construct, for example? So putting this all together is, essentially you're just matching what the load can do and is willing to do with the needs of the grid. So this is not unlike what generator flexibility is able to provide, but fundamentally it's that matching between the capabilities along these 4 hows with the needs of the grid. And for data centers specifically, there's ability to shift the compute load, which potentially decreases the uptime, and there are challenges with this that we've discussed previously, but there are multiple mechanisms to have that flexibility. So that's more of a direct curtailing your computational processes. But of course, there are other non-compute impacts as well. There are non-compute workloads that for many data centers could be quite sizable. 20, 30, 40% of the electricity consumption in some hours and locations are non-compute associated with HVAC, for example, air conditioning. Of course, there are challenges with that in terms of equipment risk, the duration and the frequency and timing in which you're able to call upon that flexibility. And as we noted before, the use of co-located resources is another way to enable that flexibility for data centers. Although, there are capital expenditures, there are air permits, and there are other kind of technical factors associated with your backup resource that might be required. No matter what is happening behind the meter, I think one of the themes that we're hearing is the dependability, transparency, enforceability from the grid operator perspective is critical. So how does that arrangement manifest itself is a key consideration here. With that, I'm sure many people here are seeing in the news a lot of activity around thinking through these different load flexibility mechanisms, how to implement them. I've listed a few major ones that we're tracking at least. One is the DOE Speed to Power Initiative and the associated, ANOPR letter to FERC that was just put out there 2 weeks ago. And just reading this quote quickly, that ANOPR includes many principles, one of which is the interconnection study of large loads that agree to be curtailable and hybrid, that's the co-located aspect, facilities that agree to be curtailable and dispatchable should be expedited. So really, that's all around the theme of speed to power. If you enable some flexibility, perhaps it could reduce the burden on the interconnection side. Texas Senate Bill 6 has several provisions. Some of them are associated with flexibility and this speed to power trade-off, and many other states are exploring similar aspects of flexibility, especially how they translate to cost allocation across all load-serving entities and all loads within certain regions. SPP is doing a lot of activity on looking at high impact large loads. Those are hills that they call it, and several options. I'll have a next slide here to kind of show off some of the proposed new processes that they are implementing. PJM has also been very active in this area, and by the end of the year should have some filings around this issue and some additional proposals in addition to the NCBL or non-capacity backed load that ultimately was dropped. And of course, there are a growing number of agreements around primarily demand response type programs with tech firms and facilities and utilities, and many new business innovations around data center pilots and design to add up on-site resources or other software solutions for flexibilities. This is a very fast-moving environment, but the team is tracking some of the key ones here. As promised, the SPP proposal process, this is just an example. SPP presented this at our workshop last week. And you can see in this flow chart a few things. One is a very short 90-day study commitment on the interconnection side, as well as an ability on the chills. You can see in the first turquoise one here, an ability to connect immediately for curtailable service for a standard 5-year term with that conditional flexibility provision. There are new ones around HILGA. The G stands for generator, so that's the on-site resource. If you have an on-site resource, they're developing processes to study those resources and load together. And not shown on this flow chart, but SPP also has their price adaptive load, which applies to all loads, not just large loads, but to really have more of a price signal base, not really dealing with interconnections, but really having that faster response on kind of the market operations time scale. So with that, just closing out with one slide here, there have been, of course, numerous conversations around flexibility. Some of the themes and threads that we're picking up from all this are listed on this slide. One is that focus on speed to power. As we noted before, some of the economic incentives are challenging given the business model of some of the data centers and large loads. So really, it's that speed to power has been one of the primary focuses of or foci of flexibility from large loads. The second one is really on the need to think about flexibility up front at the beginning process of data center or large load design. We're hearing that it's difficult to retrofit or have flexibility later on. And to me, what this means is having some standardization and agreements around flexibility early on is necessary, given the rate of growth that we're seeing with data centers. On the third bullet, we're also hearing that, of course, not all large loads are the same. There's really a lot of heterogeneity in terms of the loads themselves and therefore the flexibility capabilities. So really, are we targeting different large loads? Or the rules really need custom made for different load classes or load types, or should there be more universal rules? The fourth one here is one that our load forecasting team has identified, which is load flexibility is rarely considered in the load forecast, which could lead to a different outcome in terms of peak load growth than you might expect. And in addition, since load forecasts are on the beginning of many of the planning analysis, both for resource and transmission planning, it could really have a material impact downstream on what you develop, what you procure, and all the questions around, stranded assets and, efficiently designing the system. The second to last bullet here is around those specifications that I mentioned earlier, really understanding, what loads are willing and capable of providing in terms of flexibility for these different services, and then therefore incentivizing them appropriately. It's that coordination between the grid and the grid operators versus the load that becomes critical. One of the quotes that we have here is flexibility without coordination is potentially worse than no flexibility at all. So really having clear specifications on those commitments. And in terms of the incentives, there's a large discussion occurring over whether or not flexibility should be incentivized versus required or mandated. Ultimately, kind of where we land is a combination of both. And what that means is exemplified by some of the work that is being done at EPRI in their DC Flex initiative. This is all under development, but one thought that is occurring is maybe there's a tier of flexibility where different benefits are associated with different levels of flexibility. On the first one, really, it's flexibility just to support during grid disturbances, from an RA construct, for example. And all the way at the bottom, flexibility means, a fully dispatchable resource like you would have with a generator. And with those tiers could come different benefits, and hence what we're calling here carrot sticks in order to identify those. And with that, just want to thank you. Our contact numbers, our emails are here, and I'll turn it back to you, Eric.
All right. Thanks, Trieu. Thanks, Julia. So we do have a number of questions that people are adding, and I just encourage folks to keep entering your questions and upvoting ones that you like. So looking through these, I'm going to try to find ones that I think are of most interest to the other audience and that we might have some good questions for first. So one I had, so I guess the first one was just talk maybe for you, Julia. Question is, as you were discussing with large loads showing a similar behavior to inverter-based resource generators, is it possible to apply some of the IBR connection requirements in the same way to these large loads as well?
It's a good question, and I think in some sense it's good to think about it that way in terms of grid impacts and characteristics that are needed, for good grid behavior. But on the other hand, large load is not a resource; it's a customer for the grid, and so therefore there is kind of, I guess, regulatory limitation on what can be required. This is, again, kind of new area. It's not really clear what the capabilities are. So we are trying to figure it out right now. But I think it's a good start. So kind of good start to think about why these IBR requirements are there, what was the motivation behind it. And then from that point on, think about, what do I need from large power electronic loads? And then the next question is, what are they capable of? And then kind of try to meet somewhere in the middle. And I think some utilities, some system operators already started on that route, kind of following that path.
Great, thanks. And another one, I think for you, Julia, you were talking about how, particularly during training for AI, that there's oscillations that have been observed. I don't know if this is something you have seen, sort of what some of the reasons are for that, or sort of what causes that during the training phase that has.
Yeah, it's just kind of a training process itself causes this kind of like rapid changes in power consumption of this large resources, and then when the training process stops, then there is this rapid drop in consumption, and then there is maybe a period when this is not happening, and then restarts again. And so people are currently looking for different ways to mitigate it, either from the process perspective, that this seems to be more challenging. Some other methods to address this that people looking at are to have additional devices, so maybe some kind of storage that evens out these oscillations. I believe Tesla had a presentation in Large Load Task Force webinar early on this mitigation measure. And then there are others that kind of maybe less environmentally friendly, is to have kind of a dummy process running in compute dummy process that evens out this oscillation, so they don't appear on the grid, but that's kind of a little bit waste of energy, and therefore maybe not a long-term solution to this.
Kind of related, I might kick this over to Trieu. Just a question on sort of what we're seeing, or what we anticipate in the difference in flexibility based on whether the AI data center is in training, or inference, providing some of the results back. Is there anything you can share on just what we might expect for the difference of how much flexibility they can provide in each of those different modes?
Yeah, I certainly think that we're hearing that the use of the data center could really impact their willingness to provide flexibility. So that certainly is occurring. And I think that the discussion is, how much should grid planners and operators, dig deep into those different use cases and develop kind of programs that fit different classes and different uses, or have a more standard and neutral set of products that they are able to offer, and the tier structure, as I noted earlier, and load customers could sign up for the ones that fit their use case more. I think that's still evolving, and we'll see what occurs. But the prime example, not with AI but with crypto, is they behave very differently than other data centers. They're much more price responsive, so they will have different impacts. So we're seeing that happening, that heterogeneity happening. It's just, how do we set up the system that meets the needs of the grids and all the customers in an equitable way?
Okay, thanks, Trieu. This next question is one that might be at one of our next upcoming ESIG task forces, so I'll share a little bit, but maybe first I want to see if, Julia, you have any thoughts on this. The question's asking, if ISOs or balancing authorities are, restricting ramp rates for any data centers. Have you heard of anything like that yet? Maybe just starting to be discussed, but anything that you've heard from folks you've talked to that are actually imposing those?
Eric, so here maybe it's a terminology question too. Oftentimes ramp rates is being used in two contexts, so maybe operational context, saying so many megawatt per second or per minute, or sometimes in conjunction with large loads, ramp rates are also being used, kind of longer term trajectories of how the given site that already have become operational is ramping up its consumption. So I'm not sure if
this one's,
that
I
question.
think, the former. It's talking about frequency and ACE. So.
Yeah, so there, I believe there are some requirements already coming out of some utilities trying to limit, and it's almost not in terms of ramp rate itself, but to try to avoid this amplitude to reduce amplitude of oscillations. That's where I've seen. So ISO and some other utilities have released requirements that are trying to just limit how much the amplitude of oscillations is. So I think, yeah, that's coming because this is kind of reliability concern for system operators.
Maybe if I can, as the moderator, share some thoughts and we have an upcoming session actually in a couple of weeks talking about whether these large loads can impact the actual ancillary services that you might require due to either their impacts on frequency from a variability ramping perspective or the loss of a large load or multiple large loads at one instant, and whether sort of a downward contingency over frequency response kind of a service might be necessary. Some of the things that NERC has already shared and folks are starting to think about whether it's something that might be necessary in the future. Next question, I guess sort of around measurements of event data. Is PMUs the best approach for measuring this? Are there other options out there? Julie, any thoughts there?
Yeah, so I mean, PMUs and point of wave measurements or some kind of disturbance fault recorders or things like that are being named right now, and that's again kind of similar to what's required from IBRs. I think both, I've seen the question in Slido, both are needed. PMUs are more expensive in terms of hardware upfront costs, installation costs, but PMUs are more manageable to provide continuous monitoring. And so that becomes helpful, say, for detection of oscillations and things like that. And also at initial event analysis, so where events are happening affecting multiple loads, PMU data will be kind of the first go-to to figure out what happened, who tripped and or who oscillated and things like that. Whereas the point of wave data is higher resolution. It may be already available in some existing relays. It still, needs to be activated, and data acquisition needs to be taken care of. Triggers need to be set. So kind of what kind of events you want to trigger this data saving on, so that to make sure that when you do event analysis, you can go back and retrieve this information. And because it's high resolution, the storage is much larger, and then that infrastructure is expensive. But basically, I would say similarly to IBRs, both will be needed. It's just kind of people are figuring out right now how the point of wave data collection needs to be set to make sure that we capture important events.
Okay. I think of a good way to. So I think you both mentioned throughout the presentation that we need to consider the heterogeneity of large loads. They're not just one monolith. They all create different impacts, and I think this question is kind of asking about that in terms of maybe I'll sort of use the question in a way of like what can we learn from there are large loads, and I think they used a good example of arc furnaces, and many areas have experienced the volatility in arc furnaces, and sometimes the price sensitivity of arc furnaces to reduce consumption during high prices and things like that. Can we use any of that to help with this analysis? Like, is there enough similarities of things that we have a lot of experience on that can be used, or is it really we're focusing on sort of the characteristics that we're just don't have that much experience on? Hopefully I asked that in a way that makes sense.
Yeah, maybe I'll get a start on that. I think there are similarities and differences. So both within comparing new large loads with old and amongst the different types of new large loads. We've already touched on, AI training versus AI use in crypto, et cetera. But, that means that there's also similarities from existing large loads that we can borrow from, right? Just the world is quite different today with the demand to be interconnected faster, and the supply constraints, demands a different thinking around integrating new large loads. The power electronics interface is obviously a major difference that, we can't learn much from existing large loads, although we can learn from, IBR on the generation side. So that is happening as well. So that's not much of an answer, Eric. I think you really have to look at component by component. The speed and scale is also something that is, there's no real historical precedent if the forecasts are correct of this kind of integration. Julia, I don't know if you have more to add.
Yeah, just kind of similar kind of thing. I think we looked into this during our spring workshop. We actually had a presentation kind of looking into history of how we dealt with steel mills and arc furnaces before. And I think one of the differences is that those were, in certain places, and there are just a few, and the utilities could deal with them kind of one by one. They didn't need to have like system-wide requirements of how they're supposed to perform, whereas this is because of the scale, because of the concentration, but also power electronic characteristics. There are differences of how we need to treat them, and we are kind of deviating towards more kind of system-wide requirements, performance requirements, and trying to model them somehow in more standardized fashion to make it more manageable.
Sorry, Julia, just to add, I mean, it's a speed, scale, and uncertainty. Before large loads, you would have one customer that would deal with the utility and have that arrangement. Now you have, interconnection queues for large loads that are growing in multiple areas, some of which may be more speculative or exploratory. That makes it hard to plan for it, and it makes it hard to forecast for when it will be hitting and where.
True. This is, I think, a question that sort of, we've seen some of this, I think, with some of the proposals at SPP and in Texas with SB6. So I'm going to ask the question, maybe ask it also a little bit differently. They're asking, maybe what is our view on introducing these minimum flexibility requirements as part of connection. So think about that. But I'm going to ask it one step further, just to maybe make it a little more interesting, is how would you actually do that? Like, what's the metric of minimum flexibility that you would use? So if these, if we're talking about, speed to power and flexibility as a requirement of, getting connected more quickly, how do you define what flexibility is using what type of metric?
Yeah, that's a great question, Eric. I think I'll get to your question eventually, but I think that, the initial question is what's happening out there in terms of minimum requirements. And I think that is really active discussion. I don't think we've settled as an industry on one minimum requirement yet. The examples that I showed really are within the past couple weeks or months that these things are emerging. So there's an exploratory phase that I believe everyone is going through, and where we land is a big question mark. The EPRI DC Flex tiers is one way where you kind of give these different options in terms of level of flexibility for different services. So in some ways, that's a balance from a minimum or requirement versus, here's a menu, you get this if you sign up for that. And I think that is a model that maybe is more amenable for the load side to be able to sign up for what they want. Of course, there's trade-offs there. And to your question, Eric, I think it really impacts the minimum should be set by what impact it has on the system, right? As we noted, we did not define a large load based on a specific megawatt size because it's relative to the impact. So one has to do the study to say, hey, if I operate in this way, I will have this impact. And therefore, if I operate a different way, I could avoid that negative impact, whether on cost, transmission upgrades, the like. So I don't think you could set a standard number, but you could set a standard process and have that cost and impact causation to define the minimum. That's my personal view, at least.
Yep. Makes sense. Well, we're about 3 minutes, so I think there's a lot of good questions on here, but I think what we'll try to do is look at them afterward and share those back. But we're about 2 minutes out, so yeah, Julia,
There was just
is there
one
you
that
really
I maybe
wanna...
wanted to publicly address. There was one question about the reports, if they will be publicly available once they finalized.
Oh yeah.
And yes, this is how it's going to be. The draft reports will not going to be available, but once we have finals, all of these reports will be in public domain on ESIG webpage.
And those of you that are already receiving ESIG emails to get webcasts like these will receive that email once that report is published, and it'll be free to the public. Yeah, and keep watching for other ones that come out as Julia showed some of the publication dates that we're planning on in the whole series. So should be a lot of good things coming out, not only from ESIG, but from many other organizations that are working on these topics. So thanks everyone for joining the call. I just want to thank Trieu and Julia again for going through those slides and sharing the thoughts on this first introductory report on the Large Loads Task Force. I'll also say if you are an ESIG member and are working on large loads in any of those project team areas that Julia showed and are not part of the task force, would like to get more of that information to kind of see, as things are going or participate. Some of the project teams are already sort of had some of their last sessions, but some of them are still ongoing. Reach out to actually any of the three of us or others at ESIG to let us get you connected to that. But we appreciate everyone's participation. Look forward to seeing you all again soon at an upcoming webcast or a task force working group meeting, or maybe at the next in-person workshop, which will be in March in Tucson, Arizona. So hope to see many of you there. Further information on the webinars and meetings can be found at www.esig.energy under events, as well as in our newsletters and informational emails. So thanks again, Julia and Trieu. Thank you all for your interest, and look forward to seeing everyone again in the near future.
Thank you. Thanks.